Okay, this would be fun, right? Would we enjoy this? Some of us might be terrified to do this. Okay, it's probably pretty scary too. I actually tried to get it to be a field trip. Okay, no joke. All right, for like anyone that wanted to go, like, oh yeah, because I have some certain seniors that'll take 2 years of physics with me, and I asked the district, hey, can we go jump out of planes? Is that cool? And they definitely turned me down. They said it was too dangerous to jump out of airplanes for a physics lab. Okay, all right, free fall. Before we really start talking about gravity, let's review acceleration in general. Okay, so let's say I put that on the screen. Okay, do we know what that means? Okay, is Royce right? Every second the speed increases by 5, is that correct? Okay, that's what an acceleration of 5 means. Okay, 5 meters per second per second. Okay, here's an example data table. And we learn here through this example that velocity is super easy to deal with when we have a constant acceleration. All right, it just increases by 5 each time. And it also can decrease. Okay, when it decreases, the velocity and the acceleration have different signs. All right, so for example, if something was going in the negative direction and the acceleration was positive, okay, then we could have something where the speed is decreasing by 5 each time. Okay, so both can happen. Okay, now here is the equation we're using to get all of these things, and you know how to use it. Okay, if something starts from rest, V initial is 0, so it drops out of our equation. Okay, and all I'm doing here is doing AT a bunch of different times, multiplying by 5. Okay? All right, so we understand acceleration. Here's kind of some of the new stuff we're going to do today. Can you answer those questions? By the end of today, you should be able to answer all of those questions, okay? In pretty good detail as well. All right, you might not even know what some of these words totally mean yet, okay? But we're going to come back to this slide at the end of the presentation. Okay, there's Galileo, all right? Legend has it that he went up on the Leaning Tower and just started dropping stuff off. Would you be allowed to do that today? You would get arrested. Okay, so he's up there doing physics experiments, dropping stuff off stuff. All right, we did a lab last time where you dropped stuff a short distance, and you should have been able to figure out something about gravity with that. Okay, all right, so let's drop some more stuff. Okay, let's drop a book. Which one should I choose? Yeah, biology for sure. Okay, we're not going to disrespect any physics books today. Okay, so we're going to do 4 little experiments, 4 races here. Okay, we'll start with this. Okay, who's going to win, book or paper? You guys all agree book? Okay, we're not surprised, right? Okay, all right. Let's do another race. Okay, option 1. They're going to fall together, like so. Okay, option 2. The paper's going to separate and beat the book to the ground. Okay, option 3. The book is going to pass the paper and the paper is going to float. Okay. Also not that surprising or impressive, correct? Okay. All right, race number 3. Okay, we've got our book, we got our paper, we're going to drop it. Option 1, they're going to fall together. Option number 2, okay, the paper's going to kind of do this and the book's going to win. All right? Option number 3, the paper is going to overtake the book, okay, and hit the ground. All right. Option 1, we're going to actually vote with hands this time. Okay, who thinks that they're going to fall together like so? Okay, I got like 5 people. All right, 6. Okay, option 2. All right, they're going to separate. Paper's going to, okay. And option 3, the paper's going to do that and win. No votes for that? Yeah, okay, there's always one. All right. Okay, here we go. Oh, they fall together. Okay, this is surprising to a lot of people that that's what happens. Okay, so let's go back to option 1 for a second. Okay, why did this one do this and take a long time? Okay, what do we got? Air resistance. Okay, today's the first time that that kind of comes up. All right, now here's the thing. There is air resistance on both. Okay, and since they're about the same surface area, there's about the same air resistance on these. Okay, now this one is affected more by the air resistance than this is. Okay, and to explain why, we first have to know what air resistance even is. Okay, air resistance is just things running into air as they go through the air. You can have that with a falling object or even a car. Okay, so when this falls, is it running into air? Yes. Okay, but the mass of this is so great that it's not affected very much by the air, because the air has a lot less mass. Okay, does air have mass though? Yes. Okay, now this one, this is affected a lot by the air that it's running into because its mass is so small. All right, and its surface area is big, so it's hitting a lot of air. Okay, let's do one more race. Okay, physics rooms are kind of cool because they have stuff like this, like gas pipes. All right, they also have an air resistance switch. Did you guys know that? Okay, they're usually... Okay, did you guys hear that? Okay, what I just did was turned off air resistance. There's no more air resistance in the room. Okay, we're going to race them again. All right, what's going to happen? Let's see. 3, 2, 1. What happened? They hit at the same time. Okay? Did you guys pick up on the sarcasm though? Okay, what would happen if I could turn off air resistance? What would happen to us? We would die. Yeah, bad stuff. Okay? But in a way, okay, we can reduce air resistance by making it look like this. And then they basically hit at the same time. Okay, so what we need to know here is that gravity accelerates things at the same rate, okay, independent of mass, as long as air resistance is not a key factor. Okay? And we'll do more with that on the screen here in just a second. Okay? First, I'd like to show you guys this because we do actually have an air resistance switch. Okay, this time I'm not lying to you. Okay, so we got this little pipe here. Okay, and check this out. Okay, we got a orange feather in there, and we got a dime. All right, and same as experiment number 1 up there. Okay, there's air resistance affecting one more than the other. Okay, here's my air resistance switch. It's called a vacuum pump. All right, it's pulling all of the air out of here. Okay, there's a little gauge on there that tells me when most of the air is gone. Okay, so now we can seal it off. We got a valve. Yeah. Okay, and so We have now taken this to space-like conditions. Okay, is there gravity in space? Okay, there is gravity in space. Okay, a lot of people think that there's not. Okay, what there is not in space is what? Air. That's what space is. Nothing. There's nothing there. That's why we call it space. Okay, now check this out. Look at that. Are they basically tying? Okay, so we have taken air resistance out as a factor. All right. Now, the reason why they don't exactly tie is because this thing is not perfect at getting all of the air out. There's still some air in there. Okay. In addition, the feather kind of drags along the side sometimes. All right. There's more friction against the side. Okay. But basically, this proves that mass doesn't matter for acceleration. All right. As long as there's no air. Okay. Oh yeah, we can also do this. Okay, this is kind of fun. We can let the atmosphere back in. Okay, just kind of proves that, all right, the air was gone and now it's back. Okay, and they did this for us on the moon. Sound. That's Mr. Hicks talking at the same time. Okay, there you go. Okay, no big deal. We're just on the moon dropping stuff. Okay, so you guys can try this out at home. Okay, all right. Take like a penny and a golf ball. All right, air resistance is not going to become a factor. All right, with those two things, you go up on like your balcony, all right, or somewhere where you got a little height, okay, and drop them off. What should you see? Same time. Okay, go make it fun. Get a bowling ball, go drop it off. Okay, don't get in trouble though. All right, and you can race different things. All right, and you'll see that they will accelerate the same independent of their mass. All right, now you start putting light things in there like a ping pong ball. Okay, what factor is going to come into play? Air resistance. So we need to be good at noticing when we can leave air resistance out and when we have to pay attention to it. Okay, so all things do accelerate at the same rate. What rate is that? This is the answer to one of those questions. And here's the answer. The acceleration of gravity is negative 9.8 meters per second squared. And we're on part 4 notes if you haven't found that page for free fall. Okay, free fall notes part 4. Sometimes we will call this little g. All right, little g, we'll say that all the time. Little g is negative 9.8. Okay, now the negative part. The negative we put in there because in physics we like to call the down direction negative and up positive. Okay, helps us all to stay on the same page with directions because these are all vectors. Direction matters. Okay, here's little g in a different unit, negative 32. All right, that's feet per second squared. We won't really use that, but I just put that up there to show you that there's different units we can be in. In our lab, okay, we had this unit for little g. And, oh yeah, what value is good here if you're in millimeters per dot squared? Should be in like the low 2s somewhere, 2.5, okay, for your slope of your graph. Then when you convert it, should be close to 9.8. Okay, so a couple more things with that. You might see this. Okay, this is just little g taken out one place past the decimal. To make the math easy, sometimes we will round little g to negative 10, all right, to make our numbers friendly. And those are the things you're going to see. This applies to the surface of the earth. Okay, now we go up to the moon. Is little g still the same value? The moon has its own little g value of about negative 1.6. Okay, that's the surface of the moon. So it depends on where you are. Just like before, a table. Let's say we drop something. Okay, it starts at a velocity of 0. Every second that goes by, it's going to pick up a negative 10. Okay, it is speeding up in the negative direction. Here's an example. They have parachutes, don't worry. Don't try that. It's illegal in the United States anyway. Okay, did anyone catch the country there? Yeah, Norway. They're allowed to do that kind of stuff in Norway. So, okay, now if I play that again, check this out. All right, they got parachutes. This is a sport called base jumping. I guess you could call it a sport. Well, look at this. Okay, 10 meters per second every second is what's going on. Okay? All right, so far we've talked about dropped objects. And in all of these examples, okay, what is the initial velocity for a dropped object? Okay, it's real easy, it's 0. But we're also going to do some stuff where we throw stuff up in the air, okay, like this cannon. So if we shoot a cannonball straight up, okay, that's going to happen, right? It's going to go right back into the cannon, right? Okay. Now, on the way up, okay, for this or for a ball, on the way up, is that free fall? Okay? How you know it's free fall is gravity is the only thing in control. That's the definition of free fall, is that gravity is the only force. Okay? Now, on its way up, is gravity in control? Answer is yes, it is. And I'm not talking about the throwing motion. Okay, the throwing motion, I'm producing a force on it. But the instant it leaves my hand, gravity's in control. Okay, so now in physics, okay, things on their way up are falling objects. Okay, and that might be a little bit like, okay, so on its way up, it is falling. All right, it's kind of weird to say, but it's true. Okay, little g is in control. All right. 2 seconds up, 2 seconds down. Okay, let's say we shoot this at 50 meters per second. How much time to get to the top? Okay, let's watch. Okay, it will take 5 seconds up, 5 seconds back down. Total hang time of 10 seconds. You notice this right here, this doesn't take into account the negative direction. This is a speedometer, all right? It measures scalar speed. Okay, now this takes into account the negative. So what might we call it? Hint, it's measuring velocity. So we would call this instrument a velocirometer. Okay, not really a real word, but it's fun to say. Okay, so on the way up, notice its speed is going down to 0, and now it is speeding up in the negative direction. Okay, and you guys drew a graph of a falling object. Okay, here's the graph of an object thrown up, all right? Maybe predict on your pages how you would sketch that. Okay, what's it going to look like? A velocity time graph. Is it going to be straight? Is it going to be curved? Where's it going to start? Where's it going to end? Is it an easy graph? Is it complicated? I would maybe start with what value? Okay, so time equals 0. What's the velocity at time equals 0? It's 50. Okay, we're not counting the cannon part, remember? We're only counting the free fall part. So the instant it leaves the cannon, it's going positive 50 up. Okay, then what's its velocity at the top? 0. What's its velocity when it's right here? Negative 50. Okay, so here's the graph. Goes from 50 to 0 to negative 50. So it's just a straight line. All right, now people want to make it curved and all complicated. All right, but we got to remember what the slope of this graph means. Okay, any velocity time graph, what's the slope give you? Acceleration. And we just said that this whole time the acceleration is negative 10. All right, gravity's in control the whole time, even when it's at the top. Okay, so that means the slope of this line has to be the same everywhere. Slope's got to be negative 10 the whole time because gravity's in control. Okay, now the top is particularly weird for people. All right, what is the velocity at the top? 0, okay? Now, let's say gravity decided not to act anymore once it got to the top. Okay, what would happen to the ball if gravity was not negative 10 at the top? It would stop. You'd throw it up, and it would just stay there. Okay, that doesn't happen because it's still in free fall. Gravity's just in the process of turning it back around. Okay, Maddie? Yep, if I bounce it, same thing. Okay, the second it leaves the ground, it's in free fall. Okay, now the bouncing part, or the throwing part, or the cannon part, we study that later. Okay, we're not talking about any of that. Okay, great question. Okay, we're also going to do some of this. All right, we might not start at ground level. We might be up here and launch something. Okay, we might even do this. We might take the cannon and turn it around. We might shoot it downward and analyze that physics. All of those situations are free fall. Okay, so if I take my tennis ball, okay, and I throw it down, okay, the instant it leaves my hand, it's a falling object. Okay, I just gave gravity a little head start and gave it a negative velocity to start. Okay? All right, 2 videos to kind of end this section with. Okay, I think you'll like these.
Our current understanding of gravity is based on the general theory of relativity. It was developed when Albert Einstein realized that a man in the emptiness of space would not be able to detect whether he was falling under gravity. Einstein called this a happy idea. But in 1960, 5 years after Einstein's death, Joe Kittinger made the idea a reality. He was part of a US Air Force team studying the effects of high altitude on the human body. He never achieved the fame of Yuri Gagarin or Neil Armstrong. But to all intents and purposes, Joe Kittinger was the first man in space. balloon was 30 kilometers above the Earth, 3 times higher than a jet airliner. And then, carrying a film camera, Kittinger did something amazing. He jumped. High above the clouds in the incredibly thin air, Kittinger had no sense of falling. He had to look back up at the receding balloon. But he was actually accelerating to 990 kilometers per hour. Only after decelerating in the thicker air lower down did he open his parachute. Kittinger was the first man to reach the speed of sound without an aircraft. But in this astonishing encounter, gravity did him no harm at all.
Okay, is that complicated physics right there? Okay, it's just that. All right? But from way way up, that's all it is. Okay? So, that might be kind of surprising to some of us. Let's take a look at this real quick. Okay, there's the Earth. All right? Okay, now how big should I make the atmosphere? If that's the Earth, how thick should I make the atmosphere? Like how tall above the Earth? 9.5 inches? Why are you saying inches? Can't we keep it like clean and metric? Okay, so like guys, it's like that thick. That's about, okay? If I'm to estimate with just expo markers, that's about how thick the atmosphere is around the whole Earth. Okay, kind of surprising maybe. So Joe, all right, he was like maybe right there. Okay, just barely above the atmosphere. Was he in space? Pretty much. Yeah, they said he was, for all intents and purposes, he was the first man in space. Okay, so he just did a really long free fall. All right, about that far. That's not even that far. Come on, Joe. Okay, all right, just a really high altitude free fall is what that was. Okay, now a lot of us think that if we put something up in space, okay, let's put something up there. Okay, what's it going to do? Maybe it's just going to stay there. It will just fall. Okay, you take something from here, you put it up there, all right, it will fall straight. Okay, we got a lot of stuff up there that's not doing that. We call those things what? Satellites. Okay, so to get them to go around, that's a whole nother day. Okay, that's like in January. All right, but the short answer is we got to give them a horizontal velocity to get them to go around and stay going around. Okay, we're going to learn that, but baby steps. Okay, all right, now there's a modern day video of this. Okay, I think you'll like it even better. Okay, sponsored by Red Bull there. All right, did you see the old guy? Okay, that was the original guy from the first video. That was Joe Kittinger. Okay, so Felix beat some records, I think maybe for height, and then the max speed he got up to and stuff like that. Okay, that was in I think 2013. We got to watch it live in physics class. It was super cool. Okay, now there is one complication worth mentioning here. Okay, we kind of oversimplified it if we said it's just that. Okay, when things fall for a long time through air, what do we have to take into account? Air resistance. Okay, so it's not quite as simple as just that. All right, air resistance is going to be a big factor that we'll have to deal with, but we'll deal with that next year in AP Physics. How about that? Yeah? Okay, you guys got any questions on that?